The topic of the talk you can see in the shared screen is Dirichlet boundary optimal control problem, energy space formulation and approximation. Professor, you will be having 55 minutes, and then last 5 to 10 minutes we will keep for the comments. And I am really thankful to you to give this talk, because I'm pursuing you from last 2 years approx. Let's rock this here.
Okay. Yeah, thank you, Professor Ravi. It's a pleasure to talk today. So as you see that the title of the talk is about we are going to talk about Dirichlet boundary optimal control problem. Basically, I'm going to review some of the formulations to formulate this problem mathematically, and then we'll discuss the questions related to approximation of these problems. So this is a joint work with my former students Ramesh Ch and Sudipto Chowdhury, and recent postdoc Gouranga Mallick, and my colleague Professor Nandakumaran. The outline of the talk is as follows. So first I will tell you what is the Dirichlet boundary optimal control problem, and then I will discuss the finite element approximation for the elliptic case with the constraints on the control, and then the second part I will present about the parabolic problem, and the optimal control problem is governed by parabolic problem. So the Dirichlet boundary control problem we can see as follows. So suppose we want to heat a body to a certain given temperature, UD. UD is a given temperature, for example. So that's called the desired state. You want to get the body heated to close to UD by applying the heat source on the boundary. So basically the heat source is coming from the boundary, so that we achieve internally the temperature U, which is close to the given desired temperature UT. So it could be temperature depending on the physics of the problem. So mathematically, when we want to see it, given there is a function UD, you want to get the solution U close to UD by appropriately finding the Q, which is only defined on the boundary. So mathematically, can see the problem is posed as follows. So we would like to find a state, that is U, and the control Q, which is these two. The tuple is minimizing the quadratic energy functional, which is defined here. J of y comma p is half of the distance between y and UD in L2 norm, and plus some regularizing term. Rho is a real number, positive, and some appropriate space for the function p. So, and here y and p are linked through the PDE here. So minus Laplacian of y equal to f. F is another, maybe say f could be 0 or some internal source. And basically, y and p are linked through this boundary condition, which is known as Dirichlet boundary condition. That's why you see that Dirichlet boundary control problem. So we need to find the candidate for the boundary data, which is Q, and the state solving this equation. So we are considering the simple physical situation that it is a stationary heating process. So you can have different physics, and then the equation may be different. And also one can think in a more general setting that we don't want to heat, for example, the pose that equation y equal to p on the whole part of the boundary, but we can just think restrict this condition only part of the boundary. Like you can see that the mixed boundary value problem. So you could have a different boundary condition on part of the boundary, and the remaining part of the boundary you could have this Dirichlet boundary condition. So more general setting is possible. So now the question is, what is the right control space Q for addressing this question? Okay, so because we are going to minimize energy functional here, so when we minimize a quadratic functional, basically we would like to have some conditions based on the derivative. So differentiability is of the functional is what we prefer. So then the natural choice or the most popular approach is to use the L2 space defined on the boundary. So basically P is defined on the boundary, so ask that P is in L2, square integrable on the boundary. But you see that the PDE that we are looking is the second order PDE, and usually the the function space for this kind of problems for y is the trace space for that is much bigger, much smaller than h of. It should be more regular than L2. Okay, so but if we are only if you restrict to this L2 omega, so we cannot use the standard weak formulation that is used basically for the Lax-Milgram lemma H1 space. So that cannot be used, but one can still go further weak formulations. So the standard formulation is that you multiply this equation with the v on both sides and integrate over omega and apply integration by parts. So that will be gradient of y times gradient of v, the test function. But that formulation is not, because if y is in h1, the trace of that should be h of, but the trace is only we are assuming it is in L2. So this is addressed by further going to the another further weak formulation. So you only look for y is in L2 for given p on the L2 on the boundary by this weak formulation. So this, if you take any z in L2 omega and you take the inner product yz and then z equal to minus Laplacian of psi, you can look for a psi given z in L2. You can look for psi, which is zero boundary conditions, and then if you plug here minus Laplacian of psi and do the integration by parts twice, so minus Laplacian y will come, that will be f, and then the integration by part also will give you the boundary terms. So one of the boundary term will be 0, will be vanishing because psi equal to 0 on the boundary, and the other boundary term is this. So we get p and del psi by del n. So you can see that, so the problem can be posed, the PD problem can be posed as given p in L2. Now because p is in L2 on the boundary, this term makes sense provided this function del psi by del n is L2 and f is L2. So, and then psi, this is a solution of a second order problem. This would be in L2, and then this looks like this, we can make this possible provided that del psi by del n is also a square integrable on the boundary. So that is possible if because the psi is coming from a solution of a PDE. So if you assume that the boundary of this del omega is say convex, then the psi will be in H2, and then the normal derivative will be having h of regularity, which is much more than L2. I mean, little more than L2, which is what. So that you can see that this need to be L2, so that we can, and also it is possible to have, you can use the regularity theory on much more general domains. For example, if the domain is polygon with the one side boundary, then it is h3 by 2 plus epsilon. So still this is L2. So you can, this approach, this formulation makes sense on the domains with with which maybe Lipschitz boundary is enough. So then we can write mathematically, we can write the optimal control problem that we started. Find a state U, which is what we want, and then control Q, which is the boundary source function, minimizing this cost functional subject to this PD. Now PD is minus Laplacian y equal to f and y equal to p on the boundary. That is written much weaker sense because mathematically we have to give validity of the PD. So that which is done in this way, and here z and psi are linked through another PDE here, and j is defined now here. Q is replaced by L2 on the boundary, and alpha is the regularizing parameter. So we can show that if the domain is Lipschitz, then this is L2, this is L2, and this is L2 on the boundary, this is L2 on omega, and everything is a continuous linear functional on for given z in L2. So it's a continuous linear functional on L2. So, and this is a inner product and L2. So the solution exists. Y, the solution Y exists for given P. So the problem is well posed, but it is posed only on L2. Okay, so this approach gives a way to handle this problem, but and also we can derive now that the existence and uniqueness of the solution UQ can be proved using the standard techniques that are known in the optimal control theory. Once you know that given P there is a unique solution Y, and you have this strict convex functional, so this optimal control problem will have a unique solution. Then for other purpose, for example, for numerical point of view, we need to know exactly what is this U and Q is going to satisfy, because this is still in the optimization sense. But if you derive the optimality conditions, so we can see that the optimal state, which is the U and then control Q, are linked through this, and there is a co-state phi defined by this relation, gradient of phi, gradient of V, U minus UD V, for all V in H10 functions. H10, I think I don't have to introduce for this audience, which is, if you don't know, it is square integral functions and whose weak derivative is L2 and having zero boundary condition. And you see the third condition is coming from the optimization that the minimum, the U and Q is minimizing the cost functional. So this is the relation between the adjoint state and the control Q. Basically, if you see that this is equal to this or equal for all phi, all P in L2 del omega, which we can write it as Q is 1 by alpha of del phi by del n, and phi is this. And as I said that Z and C are linked to the speed group. So this makes this problem is well posed, and one can use this to find a numerical approximation based on this setting. But as I said earlier, that there are some restrictions like this del C by del n to be defined, and we have and this del C by del n should be L2. So that means the size should be at least H3 by 2. So we will, we have to pose some restrictions, like we cannot have mixed boundary conditions. If you have mixed boundary condition, the solution will be somewhere H1 plus epsilon. Epsilon could be less than half. So it puts some limitations on the formulation. So, and the other thing is that here del phi by del n, the optimal control Q is 1 by alpha of del phi by del n, and phi is having zero boundary conditions. So if you have corner in the domain, but even it could be a convex corner or reentrant corner. So in the reentrant corner is not possible because of del C by del n is there. So the domain to be convex, and any corner if you take and phi is zero on the boundary, see that there are two independent directions, normal directions at the corner point. If you emanate from either direction, you have one normal derivative, and so because of this, so if the phi is supposed to be, if phi is nice, then and having that then two normal derivatives which having two normal independent directions and zero boundary, this will imply that phi will be the derivative of phi will be zero at the corner. So that poses that Q is zero somehow at the corner. So we'll see. I'll show you a picture that how this will it will bring some unphysical layers in the corner. So other approach is by penalization. So we see that having P in L2, directly writing Y equal to P introduce difficulties. So we have to go to the ultra weak formulation. But one can perturb this condition by this Robin condition. So add epsilon times del Y by del N. This is known as Robin condition. So it's kind of penalty. So modify the boundary condition with a suitable small parameter and then write this. So this, once we have this term here, we can go this problem, because basically the Neumann data is L2, that is fine. So we can have standard weak formulation, and we can, this problem is posed well posed for P in L2. So we can do that, but when we do numerical implementation, so we need to tune epsilon that depends on the mesh parameter h. So, but for a user, if they don't have to do analysis, right? Nobody want to do analysis and do the implementation, and based on that analysis, that epsilon will be identified. So that's the difficulty, and also the regularity of the solution y depends on epsilon, because it's a singular perturbation. It may have difficulty. So this is another, but one could use this if you can do analysis and find out what is the epsilon. And more recently, the natural choice for the control is we know that for h1 space the control the trace space is hf. So that's how the people recently they wanted to use hf space, but using directly hf space, because the norm on the hf space is the natural norm is the double integration. If you use that the norm directly in the cost functional, because that information has to get into the problem, so that through the norm. So if you use h of norm, that will lead and also that will lead in the numerical implementation, you get a dense matrix. That is one difficulty. The other difficulty is that how to have h of norm when you have corners, because the h of norm for corners is not that easy, because we had to define the norm on each straight lines, and then there are some compatibility conditions at the corner. So these things are difficulty directly using the HF norm on the in the formulation. So what they did is that they took another way, because HF norm on the HF space can be defined in a different way. Given P in HF, so you can find a harmonic extension UP in H1 such that, so this is a harmonic function. This the Laplacian of UP is 0 and U of P is P on the given P. This problem is well posed because this is the right space and then there is an H1 function. So it's a harmonic extension. Once we have this harmonic extension, because this is the function UP is nothing but the minimizer. This is it's the solution of this problem. You take the norm of the gradients of all the functions W, which the W is having this trace W equal to P and the boundary. And the minimizer of this is a harmonic function, but this is unique, so that has to be this one. And one can define h of norm by this, the gradient of the harmonic extension. This is and this norm, the way you define the gradient of UP will be equivalent to the h of norm on this, because the trace map is onto and can pick up a continuous right inverse and can show that this norm is equivalent to the actual h of norm. So one can write equivalently, not equally, but equivalently one can define h of norm and then work with that. So one can further see that if you define h of norm to be like this, and then this is, if you take the square, this is 1, and then apply the integration by parts, because Laplacian of UP is 0, we have only the boundary term, del UP by del n, and it should be UP, but UP is P there. So this is. So you can introduce now the Stegler-Poincare map, which is going from h of to h minus of by S of P is del UP by del n. Because UP is in only h1, so normal derivative can be proved that it is h minus. It's in the dual of this h of, which is h minus of. So the h of norm of P can be written in using this Stegler-Poincare operator S of P as P, and you can see here immediately that this is a positive semi-definite operator. So then the cost functional can be defined by this way. This one, the first term remains the same. In the second term, you see that it is involving the Stegler-Poincare map, and this is a non-negative. So this is a first positive non-negative function. But so this makes sense. This is fine for theoretical purpose, but when we do numerical scheme based on this, so we need to find both the state U and the control. So we'll use some space for the control and as well as some space for the state. So, but for every trial function in the control space to be lifted through harmonic extension, so that becomes quite expensive. So one has to find a clever way of implementing this, otherwise it becomes expensive. So our objective is here that to determine appropriate function space for the control and to attach a meaning to the energy cost function and derive optimal system and then discretize using elements and do the analysis of numerics. As I was saying that if you use the L2 control, the first approach, you see that I was saying that there are problems at the corners. So because the control will be normal is equal to the normal derivative of the adjoint state, which is having zero boundary condition. So that somehow forces the corners like this. If this UD is a desired state, but desired state is like this, it doesn't vanish at zero, but you see that the state is doing this, which is not desired. Whereas if you use the H1 kind of control, energy space controls, what will happen is that it's nicely, you're getting close to what's the desired state. So let us discuss our approach. So what we formulated is that we need to use energy space, but so what we thought is that use directly the H1 space. So this first term remains the same, L2 square, and then the control is coming from now the H1 space. The function is integrable and its derivative is square integrable. And now it is the gradient is taken over all omega. And the subject to PD, so we can have more general boundary condition. For example, on part of the boundary can be split into two parts, gamma D and gamma C, where gamma D is that we fix this function. It could be some non-zero function, but for simplicity, let us keep it y equal to 0. And the control is this, y equal to P and gamma C. So the control is acting on this part of the boundary of the domain. And so this is y is satisfying this PD. So here y is coming from Q. Q is all H1 functions whose trace is 0 on gamma D. So that means when you restrict to the gamma D, the function is 0. And for control, the same function space, but it has constraints, because in the applications what people want is to have pointwise control and the pointwise constraints on the control, because we can invest a lot of money and get what we want, but the constraints what it imposes that we have limited source of the investment, and with that we can achieve the optimal state. So the constraints are because of that. Sometimes we cannot overeat any body or something like that. So there are constraints which in application point of view, these are so QA and QB is some constants. That the control which does not go below QA and above QB. And for because of y equal to 0 and gamma D, and these two are they will have intersection points. So to have this space, the set QAD non-empty, for compatibility we need to assume that QA is negative constant and QB is positive constant. So this is now minimizing, state is coming from this space and then control is coming from this set. This is a closed convex set of Q, subset of Q. And we can write the weak formulation that when you have a non-homogeneous boundary condition, this is the trick that we apply, that the solution y can be written as the sum of two functions w plus p, and w will have zero boundary condition. So when you restrict y to the boundary, it will be p. And when I search, so y has to satisfy this equation when you multiply with the test function from h10 and do the integration by parts and split this, get this. So given p, this is a known quantity, and we can ask the question of the existence of W. Okay, and bilinear forms are defined. A is defined by this gradient, the standard bilinear form, and this is the function. So Lax-Milgram lemma implies that given Q, there exists a P. So given P, there is a W, unique W that exists, and then the solution Y is given to be W plus. And we denote y to be so we introduce the solution operator S of F, and it's depending on F as well as P is 1. So we can show that there exists a unique solution for the optimal control problem posed here. because first we need to establish that given P there is a unique solution, and then you have this this solution map, and which is injective, and then this is a convex quadratic functional, strictly convex quadratic functional. So then the solution, the standard argument will give us a unique solution of the control problem. So I'll quickly give the overview of the proof, because J is non-negative because it has the norm squares, so non-negative. So the minimum exists, that you call M. But the minimum M exists, but whether this is attained by some functions is what is the question. So because there is this minimum exists, so there is a sequence Yn and Pn coming from the function spaces given here, that the product space, such that this converges to M, and Yn and Pn are linked to this solution operator. So if you look at this cost functional, it has the gradient of P. So, and this is converging to M. So this gradient of Pn is all this for all n, it is bounded. So we have a bounded sequence from there, and then also it has pointwise constraints on the control on the boundary. So this is basically Pn is bounded in full H1 norm. This is only the gradient. So it is bounded in by using Poincare inequality. You can show it is bounded. Pn is a bounded sequence in H1. So we can conclude that Pn is bounded in. So once you have a bounded sequence, it will have a convergence subsequence Pn that converges weakly to some element. Say you call it Q in small q in big Q. But since this QAD is weakly closed because it is closed and convex, and because the convergence is weak, so this is weakly closed. So the weak limit Q will be in this set QAD. Okay. So we have the candidate for the control. So, and then we need to see about the state, and Q and this Yn and Pn they are satisfying a PDE. So Yn is written as Wn plus Pn. So Wn can be proved to be bounded. The bound is given by this. This is being bound for all n. So this will be bounded, and hence Yn will be bounded. So Wn is bounded because this is H10 function. We can again extract a subsequence. Again, you denote it by Wn. So corresponding the subsequence to Pn, you can get another subsequence Wn. So that converges to W. And because we have the weak convergence and Wn and Pn are satisfying this, we can pass the limit and we get this equation. And so you can define U to be the W plus Q, the sum of the limits. This is the corresponding state. Now to show that Q and U and Q are indeed the candidates which are minimizing, attaining that M. So we use a weak-Lomer sum continuity of the norm, which gives that the gradient of Q is bounded by the lim inf of these quantities, and also that these are converging weakly in the stronger norm H1, so they converge strongly in L2. So Yn converges strongly to U. So hence we can having this. So this is Yn is converging to U, and then so we have the equation in the first part, but there is a gradient of Q which is bounded by this. So we have inequality, and this when you pass the limit, this has to be because these numbers are going to M. So we get the existence of the control and the state. Okay, uniqueness comes from the strict convexity of the cost functional, and so that's the idea of the proof. But what we want is for numerical point of view is the optimality conditions. So you look at the derivative of this reduced functional, which is defined here, J of P. So basically here it was U minus UD, but U is nothing but S of the solution for the data F and P. Okay, so everything written is in terms of P. So it is a functional just involving P. So when you look, because U and P Q are the Q is the one. When you put Q, that is the minimizer. So the derivative should be 0 in when you don't have constraint, but we have the constraints, so derivative will have a sign. At the minimum, derivative has to be bigger than or equal to 0, and in that too in the direction of p minus q. So derivative is computed here by expanding. So write the expression for the derivative and expand it using the definition, and we get this. So j prime of q in the direction of p minus q is computed like this: u minus ud. U is the optimal state, ud is the desired state, and this is the solution corresponding to the Dirichlet data p minus q. So we solve a harmonic problem with Dirichlet data p minus q, given p minus q, and we have this binding form, and this will have a sign because the minimum at the minimum this will have a sign. It's not equal to 0. Okay, this is for all p in the QA. So now because there is a solution operator here, which is not good for the computational point of view. So what we do is that define adjoint problem given u minus ud. Now because u is known to exist, and using that u and then desired state ud, we solve another problem by this. So phi is the solution of this right hand side u minus ud, and with the 0 boundary conditions. So once we have this, so we can substitute here u minus ud. We can start with the p minus q and then and subtract this s of 0 p minus q, because s of 0 p minus q and p minus q, this is also defined internally. So this have a 0 boundary condition. So if after doing some manipulations, this condition can be written as a variation inequality here. So this is the grade A is the gradient of q, gradient of p minus q, and rho is a constant. So it is a variation inequality is appearing as an optimality condition. So this is clubbing all this, combining all these things. We have a unique solution, which is state and control, and there is adjoint state phi. Okay, and then they satisfy this coupled system of equations. We see that what is actually control this one. The last equation is telling us that so this is for all p in q. This is h1 functions having some constraints on the part of the gamma c. Okay, so and then see that the so qa and qb, we assume that qa is negative and qb is positive. So we can take the functions with a 0 trace and do some arguments to show that this nothing but this q solves this Poisson equation. Laplacian of q is 0, and it is also it is imposed in the space. Q is 0 on gamma d, and q has constraints on gamma c. Okay, so when we do the integration by parts, if we assume that q has certain regularity, if you do the integration by parts here, what we get is that this will be equal to this quantity equal to 0 if p minus q is 0 on the boundary, but not necessarily, right? So if we take only those v, it is equal, but otherwise it is not. So this is tested for all p in QAD. So when you do the integration by parts with the general p and q, we get these conditions. If a q is strictly lying between q and qb, which is in the literature it is called non-contact with the constraint. So it is this is non-contact with any other thing. Then you can show that the normal derivative of q is 1 by rho times normal derivative of the adjoint state. If this is the at any point this is satisfied, this is the condition. But if q comes to the contact with the qa, if q is equal to qa, then it will have a sign. It will be non-negative. And if q is in contact with qb, then this is the sign. So this problem is a simplified Signoroni problem, which is the Signoroni problem is known in the contact mechanics for actually that is posed for the linear elasticity equation, but the constraints will be like on the normal component of that, because that's a vector valued solution. So it is when you just look at the scalar version of the the Signori problem. This is what it is actually. So it has a nice nonlinear phenomena. You have basically the non-contact region and contact region, and there could be the point that it is leaving from contact to non-contact. They are called free boundary points. So it has a nice nonlinear phenomena. And another thing is that here Laplacian of Q is a 0. So we didn't impose that Laplace, the control should have this harmonic property, but it happened that after minimizing that the control is becoming a harmonic function. That implies that the h of norm of Q will be equivalent to the gradient of Q. So what the energy realized in the formulation. So here, this is gradient of P, so which will be equal to h of norm of P. So the energy that realized is equivalent to the h of norm. So that is one to remark here. So now going to the numerical approximation. So we take the domain omega and take the regular triangulation, triangulate with the triangles, and each typical triangle is denoted by t, and its diameter is ht. And for notation convenience, right, h is maximum for all the mesh sizes of all the t's. And this VH is a set of all vertices in the triangulation. Once we have triangulation, we can collect all the vertices. And there are some vertices that sit on the gamma D and also on gamma C. This is the notation we give. And for approximating the state, which is U, we use this space. This is the V is H10. So H10 that it's so because this has polynomials, you can think these are all continuous on omega closure. And when you restrict to each triangle, it is a polynomial of degree 1. And the control space, so this space we use it for the state, basically W, where you're going to use W. U is written as W plus Q. So for W we use this because it has zero boundary condition as well. And for control we use, so it is globally continuous, and it is P1 on each polynomial of degree at most 1 on each triangle. But we have constraints on the control. So we can't use this space directly, but we use a subset QHAD, which is the elements from this space having satisfying this constraint at each node ZL. Okay, this is only, the constraint is posed only at all those vertices that fall on the gamma C. Then we can use the optimality system at continuous level and propose the discrete problem to find WH, QH, and PH. We have to find this triplet from corresponding spaces such that, so UH is written as WH plus QH. This is just algebraic identity, and then WH is satisfying this PDE, and the right hand side there is QH, and then PH is satisfying this PDE, and UH is here. UH you can write it as WH plus QH. And then QH is satisfying this inequality. There is again PH and there is again UH. So this is a coupled system of two equations and one inequality. So there is inequality, but we have posed these constraints at the nodes. So the constraint becomes finite number. Otherwise, if you have at every point, it is infinitely many constraints. So the constraints are now only finite, only at those nodes. So it becomes a numerical nonlinear approximation problem. Basically, it's a quadratic programming problem. We can use primal dual active set methods to solve such nonlinear systems. So, okay, so the analysis is error analysis is split into two parts. One is that the solution may have, the solution is already we know it is in H1, but it may, because it is a second order problem, it may have more regularity up to H2. So in the first case, we take 3/2 minus epsilon. Epsilon is between 0 and half. All the quantities U, phi, and state, adjoint state, and control. And the second part, we take this 3/2 plus epsilon. Epsilon is again like this. So we cover all the up to H2. When epsilon is off, it becomes H2. When epsilon is 0, it is just H1. So two cases. The first case, we'll discuss first, and then we discuss the second case. So the standard energy arguments, because the cost functional having the gradient of the control and the L2 norm of the state. So that is what we naturally expect to get the bounds immediately through the energy arguments. The energy arguments gives this error in the control and the state bounded by these quantities. If you look at the quantities in this on the right hand side, in the black color, these are all the interpolation errors. So this is pH can be an interpolation of Q in the H1 norm because there is H1 norm, and same for the state, with some projection of phi, and then for W as well, and then L2 norm of this. But there is, because of the last inequality, this term remains as it is. So Q, the control, continuous control, and then some discrete function. So this discrete function, ideally we want some interpolation of Q. But this cannot be equal to 0 unless we have the equation, but it is inequality, so this still remains. This is true for all pH in Qs. This is the energy arguments, give this abstract estimate. So I said that we can use nice projections here, the Galerkin projections for W and phi. So they are the Galerkin projections. The PHW minus W VH is there. So this is orthogonality with respect to the H1 inner product. This is for phi. So once we have these orthogonalities, these projections are quasi-optimal in the sense that the error there is the best, and the same thing for the W as well. So because this orthogonality, we have these are the quasi best approximations. Using them, so what ideally we want is that because this Q minus QH to of the same order as the interpolation error. So if you pick up a pH as the interpolation of Q, the interpolation theory tells that in H1 norm it is H power 1 minus 2 epsilon when we have this regularity 3 by 2 minus epsilon. Because if you measure interpolation in H1 norm, you take out 1 here basically, but you are squaring it, so it is 3 minus 2 epsilon. And so the squaring, so it is minus 2, so it will be 1 minus 2 epsilon. This is the expected order of convergence for this one norm, and this is L2 norm is of this, and this is this is the interpolation error that we know, and then this one to be expected of the same order to have the optimal order of convergence. So basically this is the dominating term, 1 minus 2 epsilon. This is the interpolation theory tells that this much approximation we can do using our spaces. Whether the numerical solution has such the interpolation estimate, the approximation property, we have to bound all these terms to the same order. So all these terms are fine except this. But if you look at this term and do the integration by parts, what we get is this boundary term basically, because the constraints are there essentially on the boundary. So if you do the integration by parts in these first two parts, and then phi is satisfying the equation. So what we get is that rho times del Q by del N minus del phi by del N phi H minus Q. And this is the duality pair between the H epsilon and the dual space of the H epsilon on the boundary. This is not the L2 net product, but the duality pairing. So ideally, when we don't have constraints, this equal to this normal derivatives coincide up to this rho. So this vanishes actually. So this is basically the error because of the constraint, nonlinear constraint. And so if you have this regularity and we apply this, this one is it is in the dual space of this space because of the regularity that we have. So this is the H epsilon dual, and this is the H epsilon on gamma C. When this is on the boundary, so if epsilon is 0, basically what we expect is if epsilon is 0, so order it will be 3 by 2, and then on the boundary we lose half approximation, so it will be 1. So that is ideal because we are using here epsilon, so that much will be lost, and which is on par with the interpolation theory. So this is trivially holds using the duality, the dual norms. So then we can get all optimal order approximation by taking the square root. This is fine. All the control and the state and the adjoint state, they have all of them have optimal rate of approximation. So I'll skip these details. But the difficult part arises when we have more regular. So more regularity should give more order of convergence. So when we have this regularity, 3 by 2 plus epsilon, the expected the convergence rate is 1 plus 2 epsilon. Because the interpolation theory gives that. As I said, that this H1 norm will take away 1 here. So this is half plus epsilon. When you square it, it is going to be 1 plus 2 epsilon. This is what we need to. But in the previous one, we had 1 minus 2 epsilon. So more regularity will give you more rate of order of convergence in the approximation theory. This is coming from approximation theory for proper interpolations. But now whether this quantity QHN has that approximation property is to be established. So now because this is H3 by 2 plus epsilon, all of them if you assume, and then so the normal derivative will be L2. Because then we can use this after integration by parts. This was earlier represented as the duality pair. Now it is the L2 and gamma C. Okay, so we can bound it by the L2 norm of this and then L2 norm of this. So again, as I said, that if you have no constraints, this will be equal to this derivative will be equal to this. So it vanishes. Now the difficulty is because of constraints. And if you apply directly the interpolation theory, so we are not going to gain anything because there is no discrete function sitting here. But there is a discrete function pH. I can take the interpolation of Q and then use the regularity of the Q at 3 by 2 plus epsilon. So you lose half, which you get only 1 plus epsilon, which is not optimal. So you lose 1 epsilon, but epsilon could be between 0 and half. So you are losing quite a lot. So this is related to the Signorioni contact problem. So there is other different, I mean, the independent research is done for the contact problems by Hill and other people to improve order of convergence for the contact problem. So this was actually quite a long-standing open problem. They have addressed in 2015. The question was that because the control Q, it has constraints, so it can come in contact with these bounds and then it will be within the, it can be strictly between the bounds. So when it comes and then leaves, and how often it comes in close and then go away. So that means like it is, if you assume that there are only finite number of such changes, then with those assumptions it was proved, but they didn't assume any finite number of those free boundary points. They proved the order of convergence to the optimal rate. So it's a very recent paper. So we used because this is very similar to that, we have adapted some the arguments. That is I'm going to tell you in the next slides. So we have the triangulation, and so we take any triangle and that has a edge with the gamma C, which is on the boundary, and define this set. X is inside the T intersection gamma C. Okay, so this is basically the points on the boundary edges sitting on the contact part. So this X will be in the set when QA is QX is strictly linear. This is at the continuous problem. And then this is a non-contact portion because it is Q is strictly lying between these points, and the contact portion is whether Q can come at a point, can be coinciding with the QA or it can coincide with the QB. So you take the union of these two, and so that is the SC. So we have two sets. Because we assume that Q is in H3 by 2 plus epsilon. When you restrict to the gamma C, it will lose off regularity. It becomes 1 plus epsilon. So it is a one-dimensional object. So then this will be continuous on the boundary. So these sets are all measurable sets because these are all inverse images of the continuous function. Right. So they are measurable sets, and then we denote their measure SC and SNC. By this modulus. So we can then prove, basically the idea is that we are not exploiting anything here. We are just using but this has epsilon derivative. Okay, so that we need to exploit basically. So this following lemma very useful in our analysis, that let He be the length of the edge T intersection gamma. So you have a triangle which is in contact with the boundary portion in the control region. And these are all the measure of SC and SNC. Assume that both of them are the measures are positive, and we can derive the L2 estimate of the sigma n, which is the del q by del n and del phi by del n. And then q prime is the tangential distribution derivative of q on the boundary. So the L2 norm of sigma n is estimated by this, and then L1 norm is like this. And similarly, the derivative of q is like this, and then in L1 norm it is like this. So let us see the proof of one of these. So let us look at the estimate for sigma n. Sigma n, the L2 norm is like basically this intersection, the integration over T intersection gamma. So this is a one-dimensional object, this is a two-dimensional object. So basically integrating on the edge square. So but on SNC, because if q is not in SNC is that it is strictly lying between the constraints, there the flux, the qa, the sigma n will be 0. Okay, so the integration will be essentially only on the contact. The non-contact portion, sigma n is 0. So then I can write this integration. Again, I can do the integration in SNC and then subtract this quantity, sigma n t, because anyway it is 0 there. I'm adding a 0 quantity. Yeah, and then but there is SC integration, so we will be basically multiplying with the area of SNC. So divide that. And now divide with this quantity, and then take the sup of that will come out, and then you get inequality. So this is now, if we replace this, can replace this by this quantity, and then that will be the basically the H epsilon norm of this function on this set. And then this is controlled by the distance of the length of basically the edge, and we have 1 plus 2 epsilon, and this is the quantity. So this is proof by exploiting that sigma n is 0. So similarly, we can do for the tangential derivative of q. So this is by writing the definition, and then the contact portion, because q in contact with the qa, but qa is a constant, so the derivative has to be 0. So again, doing that same thing, that we can subtract a 0 term and then divide by the area, and then we can control this. So this estimates, other estimates also, L1 estimates can be done in similar way. And now the idea is that the nonlinear, the error coming from the nonlinear part can be shown to be optimal like this. So by integration by parts, this is nothing but the sigma n is this quantity times this one. Now if you take pH to be the Lagrange interpolation, and then the right hand side will be equal, we can split it to all the edges. Instead of all gamma c, you can write it as sum over all the edges inside this gamma c. Okay, so now we need to estimate this on each part of the gamma c. So we can write the edge E as a sum of the length of the edge as the contact portion and non-contact portion. But you see that the proof can be split into two cases. Either we have SC or SNC, because it can happen that the Q can be strictly on an edge, it can be strictly between the bounds, or it can be completely in contact with QA or QB on a given edge, or it can happen on a given edge, it can leave, it can have in contact and then it can leave. So these two possibilities are there. So in the first case, that one of them will be, if you see this one will be 0, then you can see that either of them will be 0, because if it is if SNC has measured 0, that means SC E is this SC is nothing but E. On that case, this will be 0, because this Q will be constant and the interpolation will be nothing but the constant, so that will be 0. Otherwise, sigma n will be 0. So the first case it is trivial, and then the second case, if both have, that's basically the free boundary. So that is the most difficult one. So we can derive based on the measure of this SNC and this C. So the estimate depending on SNC if you want to control everything by SNC, we can write this way, just applying Cauchy-Schwarz and then dividing by this area and then multiplying by that, but that will be bounded by this. And we have the estimate for this quantities, right? The sigma z, this one. And if you use the quantity depending on SC, we can do this. There we can use the derivative part. So we have these two estimates. So which one to use is depending on which one is larger. So if you see that, so one of them will be at least bigger than or equal to HE by 2. And then one of them we can use because this is in the denominator. We need, this cannot be too small. So pick up whenever which one is bigger, and based on that we can control and get the estimate like this. So this is optimal estimate. So this is nicely handled by looking at the free boundary part carefully. So these are all optimal estimates. Everything is optimal. So we do the numerical experiments. We take the model problem to be defined to be like this. Here we have taken QD. QD is some given. Basically, you may want to have control to be also desired state. So this kind of modification will help us to formulate a model problem with known solution. Otherwise, there is no need of having QD. But then, so the analysis works for this, and so this nice data is taken, and the domain is just unit square, and the contact portion is only the bottom portion of the square, and the remaining is fixed. So you see that the expected order of convergence, which is 1, because the solution is H2, so we expect the order of convergence is 1 for all the 3 quantities. It's nicely matching. The conclusions is that the controls, the approach that using L2 control on the boundary, which will induce some layers in the state at the corners of the domain, which is not appropriate. And then Steklov-Poincare map, the approach is expensive for numerical point of view. And our approach gives is numerically we can handle it and handle it efficiently, and then it also gives us sufficiently smooth control. The control is also a smooth function, doesn't bring any layers in that. And also our approach is applicable when we have the cost functional to be this. Not only just L2, but gradient. If you can also have the gradient to be controlled. Basically, you want the gradient of the state to be close to the given. So this may also have the physical application. So this approach cannot be used for this kind of cost functionals, because basically this is what the quantity of interest. In that case, it may not work. But the Steklov-Poincare map approach will work. But see that the numerically it becomes expensive. So I think, do I have time, Ravi?
No, it's up. We cannot go for the parabolic one. So we can stop here and go for the comments.
Here and so we can extend basically these ideas to parabolic problem and do this. So the references are here. That the first one, this one is L2 on the boundary. This was introduced here, and also its numerical analysis studied in this paper. And this was the paper that we first came up with this formulation. And this is the paper that I was talking about, the finite element approximation of contact problems. It is a very interesting paper. And then this is the paper that they have improved estimates from the first one. And this is the one that is they propose the Steklov-Poincare approach in that. And this is our paper. We first addressed the elliptic case with the constraints and the control. And this is, we did it for the parabolic case. Thank you.
Thanks a lot, Professor. Do you have anybody have any comments, any questions? Very fast. Okay, so if nobody has, I have very quick, just one comment I want from you. So in general, we know from the classical theory, when we get the optimal control, it always is smoother than the general control applied, right? So optimal control is always bit more smoother.
Exactly.
Or bit more regular. So my question is, please comment on this. How did it help you from the FEM point of view? Because as you said, before 2014, it was considered the L2, and then it went to the weaker version, that is H half. So it went weaker. So how?
Yeah. So when we use the L2, and the control is at the normal derivative of phi. So if you are in a situation like the convex domain, then the phi is in H2, the adjoint state is in H2. So we get the control is H off on the boundary. So the state will be H1.
Yeah.
So, but H1 is the least for for any numerical point of view. Like
correct.
If you want to get an estimate in H1 norm, you don't have anything.
And even it is worse if you go for 3-dimensional problem, right?
Yes, and also like you see that the layers are coming, right? I mean, these
are at the boundary. Yes.
Yeah, I mean, this is naturally there in the model. So the defect in the model is that. So that's why then people thought like the more natural choice, maybe the stress space in some sense.
Yeah.
So yeah, that's how thought of doing. And then you see that that layers are diminished, like they disappear in our approach.
Yeah, so weakening this did not worsen the analysis for the FEM case, for the discrete case.
Sorry, repeat again.
No, I agree that this 2014 paper, which says that it is better to choose H half space as the control space. Okay, from the physical point of view, it is okay, but for the analysis, does not it became worse because we have a weaker space now?
The analysis point of view, H of space is weaker. You mean we became weaker?
Yeah.
You mean?
Yeah.
How come?
Exactly.
You will have more regularity for the state and adjoint state and control, no?
Oh, sorry. What I'm saying. It's sorry. We have more regular space. Yeah, we have more regular space actually.
Yeah, we have more regularity.
Yeah. But as you mentioned, now we have a lack of, for example, the action. It cannot be an integral, etc. Right? That thing is lost. As you mentioned, in the H half norm, something comes at in the factor below in denominator, and it is like. It's an inner product. It's not the integration, which generally happens in the L2 case.
Oh, you mean the analysis? No, the analysis is the difficulty is because of constraints. The pointwise constraints, because the control in our approach, the control is satisfying a Signaroni type problem. So when you have those pointwise constraints on the boundary, so this is called the complementarity condition in a free boundary problem. So you have in contact or in non-contact, and then there is a free boundary. That is because it's a kind of smooth function. It comes in contact and leaves. There is the regularity is lost because of the constraints actually. Okay. This we cannot avoid when we have constraints. So this is another problem because the regularity issue because of constraints actually, not because of our formulation. Yeah, correct. That I got confused there. Yes. Now, my actually only concern irregular, it is fine. But what I was thinking that if it is L2, right? So you have a integral representation, no? But if you have an H half, you don't have an integral representation, right? H half, H half. If you use, I mean, yes, if you have a smooth domain, you can still work with the H half. Yeah, then you apply the regularity and go there, right? Yeah, H half norm you can have like defined, but if you have corners, right, the H half norm, exactly, corner domains is like a piecewise defined and with some compatibility at the corners. Yeah. So working with that is complicated. So that's why this Steenberg and they have alternatively defined H half norm through this harmonic extension. Yes, but correct. That's a typical way to compensate that. I agree with you. You brought the discussion from the boundary to the interior. Yeah. So mathematically, it is like the problem is like, see, the cost function is having the Q defined all over omega. Yeah. Okay. And anyway, it's a nightmare for all of us if the computation is on the boundary. I agree with you. Yeah, I mean, they require, like they say, they use some boundary element approach and all that, but then this Teklo, they have to compute the SH, the operator So that it becomes a dense matrix actually. Then so when they solve these exterior problems, if you have exterior PD, like you have a circle disk, and then the problem is posed outside the disk with the boundary condition and the boundary of the disk. So then they convert that using the boundary element method. But then I saw that there is this Steklov map. SH is embedding in that. So computing SH, they need. I mean, it's quite hard, complicated, and it is expensive.
Yes, of course. Correct. Yeah, there are lots of things we can talk about. Nice.
Yeah,
really nice. Very nice. I think you are also ready now for this controllability thing and things like that, which Nandakumaran
now
does.
I'm getting to controllability stuff.
Correct. And there are lots of new stuffs which is really interesting now in the controllability.
They do this Remo. They do fluid structure interaction and
of course. Remo is he's actually working since last 10 years more than controllability and all. Thanks a lot. Please go on.
Even just the fluid structure interaction, just numerical approximation itself is very hard.
I remember when I was doing postdoc with Vaninathan in 2 months. He just mentioned that if you can do anything with the FEM with this fluid and solid interface thing, I will be really happy. And I left after 2 months, but I had the plan to
it's
do
very,
that.
very interesting, very challenging.
It's really interesting, and numerically, it's very the hot cake now.
Actual problem is non-linear coupling. That linear coupling itself is very hard, and non-linear coupling is like
forget about it.
Analysis wise, so computation somehow we can manage, but analysis is really hard.
One more thing I can suggest right now, which we can talk if you're interested. In place of optimal control problem through equations, considering optimal control problem or control it through the inequations, it will be also very tempting.
Inequalities, I mean, for example, there are PD papers when Sudipto was here. You have overlap with Sudipto at some point.
Just now we got in contact through WhatsApp, but I don't have next week he's talking anyway. Next week he's talking.
Okay, so there actually we have come up with papers that optimal control for the obstacle problem. So obstacle was actual obstacle function is a control.
Okay. So that's why like melting the ice, you don't know how the thing moving boundary and things like that. Okay. Nice. So I hope you can join when he's talking, then we can also talk further.
I have some traveling on 30 to 31st. If not, I'm
you told me about that. He's talking in the November 3rd or something.
3rd, okay.
Number 7. Number 2nd he's talking.
Okay, I'll be
here. So if you can join, we can take this discussion further.
Sure. Yes.
Okay, thanks a lot, Professor. It was really nice talking to you after such a long time.
Thank you for the invitation too. I mean,
You are highly welcome. See you in the next talks. Bye-bye.
Okay, bye-bye.